Welcome to Chapter 6, Part 1, Light. So in this section, we're going to talk about light, wavelength, frequency, basically what is light and how does it work. So the light we see is visible light, and so visible light is basically anything that you can see. We also have electromagnetic radiation, and light goes from short to long wavelength. So what is wavelength? If we think about a plot where we have something that looks like this, that's not really going to work. So let's try that again. So in this case, the wavelength is how long it is from peak to peak. And frequency compares something different. So on our x-axis here, we have time, and this is amplitude, which basically tells you how high a wave is. So if we were to look at a different wave, and these aren't exactly perfect, but they'll be all right. So in this case, our wavelength is going to be shorter here, but our frequency, which is this new symbol, here there's basically 2.25 waves. And here we have 1, 2, 3, 4, 5, 6 waves, approximately equal to 6 waves. So when we think about the difference between wavelength, which is this word, and this is going to be measured in meters, centimeters, nanometers, etc. So your microwave in your house has a wavelength of something specific. The light bulbs in your kitchen, in your house, in your car all have a different wavelength. The frequency is the number of cycles in a given period, and that's thought of as per seconds. So what you'll hear me say is per second or hertz. Not the car company, but in fact the unit of time. So I want to make a distinction that the unit hertz, Hz, is equal to 1 over S. You'll also see it written as S to the minus 1. I find that I don't make my negative signs for this exponent right here quite big enough. So I almost always write it as Hz for hertz or 1 over S, which is really the same thing. So when we talk about light, how we think about it moving is the wavelength or the frequency. And so it's important to note, well, how can we use this information? And so the frequency of light is the inverse of the wavelength. What does that mean? So all light, regardless of wavelength or frequency, travels at the speed of light. So c is the speed of light, which is equal to 2.998 times 10 to the 8 meters per second. This would be provided on an equation sheet or some other data. And so the speed of light is always the same, and it's related to the wavelength and the frequency of any given light. So the equation is that the speed of light is equal to the frequency times the wavelength. So speed of light equals the wavelength multiplied by the frequency. So for any known wavelength or frequency, you can find the speed of light. And the speed of light is always going to be the same. And so this tells us that we could compare different wavelengths of light. So if you look at the light spectrum, we have sound waves way out here. We have X-rays. There's a really tiny, in terms of the spectrum, this would be our visible light. And we have infrared radiation. And so this is your wavelength increases as you go from X-rays, which have short wavelengths, all the way to sound waves, which have really long wavelengths. So you don't need to memorize this. This just tells you that they're all related. But they're all related using this equation. And so if we know the speed of light, which is a standard, we could calculate the wavelength or the frequency for any other light. So let's think about that. So what is the wavelength of light in meters and nanometers emitted from a bulb with a frequency of 8.18 times 10 to the 14 hertz? So we know that the frequency is 8.18 times 10 to the 14 hertz. And we know that the equation we're going to want to use is the speed of light is equal to the wavelength times the frequency. And the speed of light is 2.998 times 10 to the 8 meters per second. So if we're solving for the wavelength is equal to the speed of light divided by the frequency. And so in this case, this equals 2.998 times 10 to the 8th meters per second divided by 8.18 times 10 to the 14 hertz. And so don't forget that hertz is also 1/seconds. So this cancels with this, and I will actually erase that and make it red so that you can still see it. So those two cancel. When you plug this into your calculator, you should get 3.67 times 10 to the -7 meters. So this is half of our answer, and so now we need to convert that to nanometers. So 3.67 times 10 to the -7 meters times, and in 1 meter, there's 1 times 10 to the 9th nanometers. And so that gives you 367 nanometers of light. So these are the two answers that you would need to provide for this answer. So we will mostly talk about the wavelength of light almost exclusively in nanometers, because that is the wavelength that kind of makes the most sense when we talk about light. So as we talk about light, we know that light is a wave. The other thing that we know about light is that it can be produced by certain things. So some objects or metals, when you heat them up, think about if you've gone into a biology lab and heated up the filament in order to streak out a colony, it turns red. If you've ever watched molten metal get poured around, so there are lots of videos about this where they heat up iron or gold and mold it into something else. Well, when you heat metal, it starts to give off light, which tells us that light can come from places other than just waves of light. So the metal that glows, this is energy being released as heat, but some portion of the energy is released as light. So what we learned, and what they learned, Max Planck learned, is that when metal objects are heated, they emit some light. But this energy of the light, this portion of the energy that is released, is related to what's called Planck's constant times the frequency of the light. So this here is Planck's constant. And this is still the frequency. So in this case, that the discrete energy that is released is a photon. So what he's trying to process is the fact that we know light is a wave. But light emitted from metals comes in discrete packages. And so when we think about that, you can kind of think about it as a blip. Or if we really think about in the digital space, we can think about pixels. So pixels are very small, tiny squares within any image. If you zoom in enough, you can see this discrete energy segment that over time looks like something else. So in 1918, he wins the Nobel Prize for this work. And so he wins the Nobel Prize for these quantas. these discrete energy bits that are related to one another over time. And so they're related through Planck's constant. I think it's important to kind of note and begin to think about the other ways that we could look at this information. And so his discrete energy, or quanta, were discovered in this way. So in 1921, the Nobel Prize is awarded for the photoelectric effect. And so the photoelectric effect is similar to the way that we discovered the photons of light. So for some metals, when light is shined upon them, electrons are ejected. So you can think about that. If you have a piece of metal and you shine light on it, you're going to eject out this electron. So one thing we do know about physics is that in order for something to be ejected, you have to input energy. So the photoelectric effect compounds or works in concert with the information from Max Planck. And so in the photoelectric effect, it talks about how much energy is required in order to eject an electron. So in order to eject an electron, we have to figure out the kinetic energy, which is related to, in this case, the energy of a photon. And this value here is called the work function. So the work function is a value that describes how tightly electrons are held. And so in order for electrons to be ejected, the work function must be overcome. What that basically means is you have to go over this energetic barrier, and that barrier is the work function. So if you look around your room, light shines on most metals. Most metals do not, in fact, generate electricity. So the movement of electrons is electricity. And so in this case, when the electrons are ejected, they are ejected with the same energy, E photon equals H nu. So the energy of these electrons is equal to E photon, which is equal to Planck's constant times the frequency of the light. So this tells us that if you have light that comes in and hits an electron, the energy at which it moves in the opposite direction is equal to the energy of this photon of light. So you can think about it kind of like pool balls. Basically, one pool ball can be the discrete photon of light. So this is how they begin to process that light behaves as both a particle and a wave. So in order for these electrons to be ejected, the photon must have a particle behavior. But we know light is a wave. And so together, these two Nobel Prizes really show us that light can behave as we can say as both a particle and a wave. And here's really the important part, but not at the same time. So the wave nature of light, in that moment, it does not function as a particle. If the light is functioning as a particle, it's not a wave. And so this imbalance or this balance between these, it is both, but not at the same time. So it could be a particle, and then it could turn back into a wave. And so when we think about light, it's both a wave and a particle. So let's calculate the energy of one photon of yellow light that has a wavelength of 589 nanometers. So we know that the energy of a photon of light is equal to Planck's constant times the frequency. Well, frequency is related to the speed of light through this equation, where the speed of light equals lambda nu. So we can solve for the frequency. So the frequency is equal to the speed of light divided by the wavelength of light. So we can now plug this into this calculation to where E photon equals hc over lambda. So all I've done is rearrange all of these equations to give us a singular equation. So Planck's constant is 6.626 times 10 to the negative 34th joule seconds. And the speed of light is 2.998 times 10 to the 8th meters per second. We're going to divide that by the wavelength, which is 589 nanometers. So when you look at this, you'll notice that a bunch of the units already cancel. So we have seconds that cancel, but our meters and nanometers don't. So we're going to go ahead and move this to the side and convert. There are 1 times 10 to the 9th nanometers and 1 meter. And when we do this, our nanometers cancels and our meters cancels. So now we can plug this into our calculator and change that back to black ink. And so in this case, when you plug this in, you would get 3.37 times 10 to the negative 19 joules is the energy of a single photon of yellow light.